Okay, we're going to look at metallic bonds and covalent bonds. We're going to first look at metallic bonds. Metallic bonds are chemical bonds that result from the attraction between metal atoms and the surrounding sea of electrons. Metals tend to have high melting points and boiling points, suggesting strong bonds between the atoms. An example would be sodium. Sodium atoms bonded with other sodium atoms. The 3s orbitals on all of the atoms overlap. This allows the outer electrons of the atoms to roam freely throughout the entire metal. The electrons are delocalized. This means that they do not belong to any one atom but move freely about the metal's network of empty atomic orbitals. The mobile electrons form a sea of electrons around the metal atoms, which are packed together in a crystal lattice. Okay, we talked about metallic bonds having a sea of electrons. That comes from the electrons that are delocalized. The metal is held together by strong forces of attraction between the positive nuclei and the delocalized electrons. In a way, they act like cement holding the positive metal ions in relatively fixed positions. The positives here are representing the nucleus, and then the red dots are representing those electrons, your sea of electron or your delocalized electrons. This is just giving you an idea. If you look at each one of the nuclei and then all the electrons that are delocalized that are around those nuclei. This is just showing some examples of metallic bonds. Iron, when you have iron atoms bonded with other iron atoms, or cobalt, when you have cobalt atoms bonding with other cobalt atoms, sodium bonded with other sodium atoms. Your metallic bonds, again, are looking at the same type of metal bonded together. The third type of bonding that we're looking at is covalent bonds. Again, the whole goal behind bonding is to make the atoms more stable. A scientist by the name of Lewis reasoned that an atom might obtain a noble gas electron configuration by sharing those electrons. The noble gas configuration was important because those noble gases are considered very stable. A chemical bond that's formed by sharing a pair of electrons is called a covalent bond. Okay, let's look at some examples of covalent bonds. Again, covalent bonds are sharing electrons. Some good examples to look at are your diatomic molecules. You remember you guys have 7 diatomic molecules that you need to know. Hydrogen is one of them. We're going to look at the Lewis structure. And the Lewis structure is when you have the element symbol surrounded by valence electrons. And in hydrogen's case, there's one valence electron right here. And then we're going to bond that with a second hydrogen, and again with its one valence electron. Well, hydrogen wants to be like helium. It would like to have a filled outer shell to be stable, and that means it only has that one energy ring, so it wants 2 electrons. So if these 2 hydrogen atoms bond together, as we're looking at in this diagram, here are our 2 electrons that are being shared. This hydrogen with its outer energy ring has 2 electrons, and then this hydrogen with its outer energy ring has 2 electrons. They're actually sharing them in order to reach a stability. If we were to look at chlorine, chlorine has 7 valence electrons. So I have 2 atoms of chlorine represented here. This electron and this electron, they're going to be shared between the 2 chlorine atoms. If you look over here at the diatomic molecule where it's formed, here are the 2 electrons that have been shared between the chlorines. Each one of these red dots again is representing an electron. So here's 2, 4, 6, 8. There's 8 electrons around this chlorine, making it very happy and stable. The second chlorine has 2, 4, 6, 8 electrons, making it stable. So forming a covalent bond where they are sharing electrons allows for that stability, that octet, to be formed. Sometimes when you look at the Lewis structures, instead of showing the 2 electrons, they'll put dashes. This dash here is showing the bond between the 2 hydrogens, and then that's representing the 2 electrons being shared. In our chlorine example, the 6 valence electrons here, the shared pair is represented by the dash. In looking at covalent bonds, you can also have multiple bonds. Again, they're trying to form a stable octet, so sometimes it's necessary to have multiple bonds to achieve a stable octet. You can have a single bond where you have 1 pair of shared electrons. You can have a double bond where there's 2 pair of shared electrons, or a triple bond where there's 3 pair of electrons being shared. An example of a triple bond is nitrogen. Nitrogen has 5 valence electrons, which are represented here and here. And then I need to form a stable octet. And so what happens is my 3 unshared electrons here, they rearrange themselves to form a triple bond. Here's my first nitrogen, and it has 2, 4, 6 electrons that are being shared, that triple bond. And then my unshared pair out here gives a total of 8 around this nitrogen. And then for the second nitrogen, again, I have 2, 4, 6 that are being shared as triple bonds, and then the other 2 out here that are unshared, giving this nitrogen 8. This is just showing you, again, those unshared pair electrons on the outside of each nitrogen, and then the 3 dashes representing those triple bonds. This again is just looking at our multiple bonds. All 3 of these examples represent diatomic molecules. We have hydrogen with a single bond, oxygen molecule with a double bond, nitrogen molecule with a triple bond. And in this particular diagram, the structure is just showing you those shared bonds. It's not showing you the unshared electrons. Okay, here are 4 examples that are showing covalent bonds. Looking at the Lewis structures, our first one here, CH4, which is methane or carbon tetrahydride. If you'll look at the red X's, they are coming from the hydrogen, and then the blue dot is coming from the carbon. And again, the goal is to be stable. So we have 2, 4, 6, 8 electrons in the outer ring for carbon, and then hydrogen again wants to be like helium. It only has 1 ring, so it can only have 2 electrons, which are represented on each one of those hydrogens. A second example is carbon dioxide. And in carbon dioxide, you'll notice there are double bonds between each carbon and oxygen. The carbon is contributing the X's, and then the oxygen is contributing the blue dots. So we have 2, 4, 6, 8 on our outer energy ring for oxygen. For carbon, there's 2, 4, 6, 8 for the outer energy ring for carbon. And then the second oxygen, again, 2, 4, 6, 8 for the oxygen here. Again, they want to be stable, so they need to form that octet. Our third example, NH3, nitrogen trihydride or ammonia. Our nitrogen is contributing the blue dots, and our hydrogen is contributing the red X. Again, hydrogen can only have 2 electrons in its outer shell, which is represented here for each one of those hydrogens. And then the nitrogen, there's 2, 4, 6, 8 around the outer ring for nitrogen. One thing I would like to point out, for NH3, the common name is ammonia. And this is a compound that you guys need to commit to memory. Much like you know water is H2O, nitrogen is commonly used in example problems that you will see throughout the remainder of the course. And a lot of times they're not going to give you nitrogen trihydride, although later in the video you are going to learn how to write the name nitrogen trihydride. Many times they use ammonia, so if you would please make a note that ammonia is NH3 and you need to have that committed to memory. And then our fourth example, boron trifluoride. The boron is contributing the red X's, and then the fluorine is contributing the blue dots. And so for our fluorine, 2, 4, 6, 8, and then that is true for each one of our fluorines. And then you'll notice this boron, there's 2, 4, 6. Boron is an exception. If you were to go into ACE or AP chemistry, they'll get into the geometry and why boron is considered an exception to not having those 8 electrons there. For our class, just know that it is an exception to the ATEC rule. Last year in biology, you were introduced to water being a polar molecule. That polar versus nonpolar covalent bonds has to do with the difference in the electronegativity values. Remember that polar covalent bonds have electronegativity difference 0.3 to 1.7, and then less than 0.3 is going to be a nonpolar covalent. With the polar bond, you've got your oxygen here with the water and our 2 hydrogens. That oxygen is able to pull those hydrogens in closer, giving you that unequal sharing, which again is what our little tug of war down here is showing us, that in the case with hydrogen and chlorine, chlorine is able to pull those electrons closer, making this an uneven sharing, versus our nonpolar, which is going to have a shared electrons there, and there's equal distance with them. Now, one element's not pulling stronger than the other. Looking at polar covalent and nonpolar covalent, if you have 2 elements bonding together in a polar covalent bond, there's that unequal attraction for that shared pair of electrons. As a result, the element that's pulling the electrons closer, this side is pulling the electrons closer, it's going to have a partial negative charge to it, whereas the other element is going to be a partially positive charge. In a nonpolar covalent bond, the electrons are shared equally. You don't have a partial charge on either side because those electrons are bonded, they're shared equally between the 2 elements. Looking at some of the characteristics for covalent bonds, it's going to depend on the polarity and whether the molecule is a covalent network. These can drastically influence the characteristics. Nonpolar covalent bonds generally are gases with low boiling points. They are not good conductors of electricity. They're non-electrolyte. Remember, there's no partial positive or negative charges, and you need those charges for conducting electricity. They're also very volatile, meaning they're going to evaporate very quickly. Polar covalent bonds generally are liquids with higher boiling points. Highly polar bonds can conduct electricity. Again, the higher polarity is going to indicate a stronger positive and negative charge. Covalent networks can have high melting points and are usually non-conductors. Again, if it has a high polarity, it can conduct electricity because of those partial charges. Okay, naming covalent bonds, you're going to name them in the order that the formula is written. In other words, for carbon dioxide, carbon is given first, so you name carbon first. Oxygen is given second, so it's the second name. And then just like with the ionic bonds, that second element, you change the ending to IDE. And then you use prefixes. You will be required to memorize these 10 prefixes and be able to use them. Mono, 1, di, 2, tri, 3, tetra, 4, penta, 5, hexa, 6, hepta, 7, octa, 8, nano, 9, deca, 10. Again, when mono is the first, such as in carbon dioxide, there's one atom of carbon, so we don't use a prefix. Mono is omitted on the first element. And then sometimes when you go to name them, you might have to adjust, keeping the A or the O on the end. For instance, monoxide, you wouldn't have monoxide, you would drop one of the O's. Pentoxide, you would drop the A to give us pentoxide versus pentaoxide. Again, for this class, however, if that's messing you up and you have the correct prefix with the correct element and the correct ending, then I would give you credit for that. So here's a practice. We have P4O10. This is telling us there are 4 phosphorus, okay? And then you would say 4, the prefix for 4 is tetra, so tetra phosphorus, the prefix, and then the name of the first element. Tetra represents the number 4, and then phosphorus is the P. Then for the oxygen, remember you're going to change the ending to IDE, so it's oxide. And then for the prefix, there are 10 atoms of oxygen, so that's going to be deca, deca oxide. And in this case, we have dropped that A so that we don't have the A and the O, but if for some reason you include it, I'm not going to mark that wrong. I'm going to recognize that. Do you know that you need to use deca and then oxide, changing that ending? So when you look at this compound, the actual name is tetraphosphorus deca oxide. Second example here consisting of nitrogen and oxygen. There are 2 atoms of nitrogen. The prefix for nitrogen, or excuse me, for 2 is di. So you're going to say dinitrogen, dinitrogen. The second one, there are 3 atoms of oxygen. You're going to change oxygen to oxide and add the prefix tri for 3, so trioxide. So N2O3, dinitrogen trioxide. One more example here. This is nitrogen and oxygen. There are no subscripts, so it's assumed to be one of each of them. Since the first element does not have any atom, it just has the one atom, mono is omitted on the first atom. You would say just nitrogen. You wouldn't say mononitrogen. Okay, and again, that only applies to the first element. For the second element, we do include the mono if there's only one atom. And in this case, there's only one atom of oxygen. We change the ending to IDE, so it's oxide. And there's only one oxygen, so it's monoxide. Nitrogen monoxide. I would like for you to pause the video and try these 5 example problems, and we will go over them in class. Okay, this time we're going to take the name and then write the formula. So we have phosphorus trichloride. There isn't any prefix on the phosphorus, so that tells me that there's only one atom of phosphorus. So I have phosphorus, the symbol is P, and there's a 1 that's understood to be here, again, because there's only one phosphorus. Trichloride, the chloride is chlorine, that's my Cl, and then the tri tells me that there's 3 atoms of chlorine. There's the subscript 3. In this example, I have dinitrogen trioxide. The di on the nitrogen tells me that there are 2 atoms of nitrogen. Nitrogen is N, and then the di is the subscript 2. So 2 atoms of nitrogen. Trioxide, the oxide is oxygen, And then the tri is 3, so there's 3 atoms of oxygen. Okay, I would like for you to pause the video and do these sample problems that I've listed. We will go over them in class, and then once you've completed these 5 practice problems, you are finished with this video.